Every electric car, every wind turbine, every guided missile depends on two elements most people have never heard of: neodymium and terbium. One nation refines over 85% of the global supply, and that is where the asymmetry begins. NdFeB, or neodymium iron boron, forms the backbone of the world's strongest permanent magnets. Its crystal lattice, measured in nanometers, locks magnetic moments in a single direction, giving rise to coercivity, the resistance to demagnetization. Neodymium's 4f electrons drive this powerful uniaxial anisotropy, an atomic scale order that keeps magnetic domains aligned even under electrical and thermal stress. But every magnet has a breaking point. At 310 degrees Celsius, the Curie temperature, the lattice's order collapses, and magnetism disappears. Long before reaching that threshold, heat steadily erodes coercivity, and each degree above room temperature means a 0.6% drop, so a typical motor can lose up to 30% of its holding force during operation. Without intervention, failure is inevitable. A single percent of terbium, introduced not throughout but at the grain boundaries, transforms the picture. This rare element forms a shell around each Ned2Fe14b grain, pinning magnetic domains and suppressing reversal. The effect is dramatic. Usable temperature margin rises by 30 to 40 degrees Celsius, and coercivity doubles, all with less than a gram of terbium per kilogram of magnet. Grain boundary diffusion enables this precision, letting terbium atoms migrate and armor each crystal. As one materials scientist puts it, a single percent of terbium is the difference between a motor that endures and one that fails. The atomic architecture of these magnets defines the limits of electrified machines. Inside every modern electric vehicle, the heartbeat is a permanent magnet synchronous motor, PMSM. The core of this machine is a stack of neodymium iron boron magnets. Each motor embeds between 0.65 and 0.85 kilograms of NdFeB alloy and is fortified with 8 to 12 grams of terbium. Tesla, BYD, and Volkswagen have all staked their profitability and production schedules on this precise chemistry. The numbers are not theoretical. Tesla Model 3 rear axle motors, BYD e-platform axles, and Volkswagen MEB drive units all fall within this narrow bill of materials window. Magnet suppliers must deliver not just mass, but exacting performance. The magnets must hold their coercivity at temperatures exceeding 150 degrees Celsius, or the entire powertrain risks failure under load. For automakers, this is not an abstract material risk. It is a direct line to the balance sheet. Procurement teams at these original equipment manufacturers negotiate annual contracts for hundreds of metric tons of NdFeB, with terbium content specified down to the gram. A spike in terbium prices by just 10% can erase 15% of a premium electric vehicle's projected profit margin. If the supply of terbium is disrupted, the fallback is to redesign motors for induction architectures. That switch comes with a penalty, up to 15% lower torque density, heavier vehicles, and a 10% hit to driving range. The cost of substitution is measured in lost efficiency and market share. Every gram of neodymium and terbium in these motors is a hedge against thermal collapse and a bet on sustained performance. For Tesla, a 3-month inventory buffer is the difference between meeting delivery targets and halting assembly lines. BYD and Volkswagen face the same reality. The invisible science inside the PMSM transforms into a visible, quantifiable risk, one that ties the fortunes of the world's largest automakers to the uncertain flows of rare earths. Offshore wind turbines draw their strength from rare earths buried deep in their cores. Each megawatt of direct drive wind power requires up to 300 kilograms of neodymium. So a single 12-megawatt turbine holds nearly 3,600 kilograms of neodymium and 30 kilograms of terbium. Multiply that by the hundreds of turbines in a modern wind farm, and the appetite for these metals grows into the thousands of tons. But the demand does not stop at the shoreline. In a smartphone, just 0.3 grams of neodymium powers the haptic motor's buzz. High-fidelity speakers in laptops and home audio systems rely on less than a gram to create sound. Hard disk drives need 2 grams to move redheads with speed and precision. In defense, missile and drone actuators use up to 1.5 kilograms of magnet alloy, with terbium added for heat resistance. From massive turbines to pocket-sized devices and military technology, rare earth magnets quietly power modern life. More than 85% of rare earth refining, especially for neodymium and terbium, takes place in one country. These metals power electric vehicles, wind turbines, and advanced defense systems, but the real bottleneck is refining, not mining. In 2010, a sudden export curb caused neodymium prices to jump 5 times, leaving Japanese automakers stranded and factories idle. That shock exposed how control over refining shapes the future of electrification. Today, a 30-day halt in Chinese rare earth exports would ripple through global supply chains. Automakers and wind developers keep only weeks of inventory. A single month's disruption could idle a quarter of Tesla's annual electric vehicle output, stall offshore wind projects, and delay defense programs. Price spikes would hit commodity markets, triggering emergency redesigns and erasing profits. The investment path is stark. Stockpiling and offtake deals can buy up to 2 years, but new refining and recycling projects, costing hundreds of millions, take 2 to 5 years to build. Research into magnet light motors and recycling offers hope, but timelines stretch a decade or more. The world's clean future now balances on neodymium and terbium. Strategic dependence shifts, but vulnerability remains. Whoever controls these metals controls tomorrow's power. The race for minerals has already begun.